So, hot off the press, 2 days ago, a group announced that they had produced in a small accelerator in Germany, I think, something called a hexaquark. So remember I say 3 quarks working together make a proton. These guys have discovered, they've done theory saying that 6 quarks together can form an object that is described as a single quantum mechanical entity called a hexaquark. And these objects have been seen before. There's a link to a paper. Hexaquarks have been seen in accelerators. In 2014, people saw a hexaquark, which is this thing. Sorry. All right, let me check move the table. I got to make sure the camera is functioning. Okay, so there was an observation in 2014 of that thing. Last 10 to the minus 23 seconds, a hexaquark. It has this interesting property. It's called a dibaryon. So baryons are protons and neutrons, the stuff of the nucleus of atoms. The dibaryon is like a pair of them existing as a single object. This has been seen before in something called Bose-Einstein condensation. And the University of Colorado was central to the detection of Bose, something predicted by Einstein in the 1930s. He and Bose, an Indian scientist, predicted that objects at the right temperature could, multi-component objects could cease being individual objects. They could behave as if they're one object. And the guys at the University of Colorado demonstrated this in 2007 and were awarded the Nobel Prize in 2011. I might have the years wrong. So there's such a thing as Bose-Einstein condensation. You can do it in the laboratory, and in fact, technology is advancing so fast, you can go to a small company in Boulder right now and buy a Bose-Einstein condensation machine that sits on this table. It costs, I don't know, $150,000. And you can get one and put it in your kitchen and do experiments with it using atoms, rubidium atoms, clustering together and so cold that they form a cluster of them form a single entity called a Bose-Einstein condensate. Well, the guys in Germany, and the paper that came out 2 days ago says the same thing can happen if you put 6 quarks together. So the Bose-Einstein discovery at the University of Colorado involved using atoms. The guys who made this announcement 2 days ago said there's a stable object, semi-stable object, that involves 6 quarks, and they were able to predict some of its properties, and it is now a candidate for being what dark matter is made of. Because quarks are everywhere in the universe, these objects might have been made in, maybe there's some stable form. I see Steve is
well, 10 to the 23rd minus 23rd seconds isn't very stable.
It isn't. But what happens after 10 to the minus 23 seconds? This object, this one up here, ceases to exist and it blows its guts out into the neighborhood. And then those quarks find partners. Maybe it's a constant process of creation and destruction, but it has energy in it. Maybe it explains, or it's matter. Yes, sir?
The quark and the anti-quark in the meson, don't they annihilate each other?
They're not the same quark. These two guys, remember there's 6 kinds of quarks, and each one has an anti-quark. So yes, you would be right if 2 tops meet. If a top quark and its antiparticle top quark meet, poof, you just get a puff of energy.
That would be a top and a bottom.
No, if a top and an anti-top.
Oh, okay.
But if a top and an anti-bottom meet, they're not the same object. They don't annihilate.
Okay.
Interesting thing here is, I know it's hard to read, but what it says is a lifetime of a proton, an isolated proton, is much longer than the age of the universe. We've never seen a proton decay. But a neutron lasts about 10 minutes, an isolated neutron. Nobody knows why that happens. So anyway, there's this recent news about an object, an exotic object that has been seen in accelerator physics, now is a candidate for being related to the dark matter question. Some of this I'm going to skim through. You can read it. The anthropic principle deals with this. Remember, we're talking about unresolved issues. Question: was the universe designed so that we could evolve so we can study it? Or is this just happens to be a hospitable world in which we evolved and we're able to study it? These are two extremes in what is called the discussion of the anthropic principle. And we're rubbing right up against spirituality here. That is, was there a designer or not? I have met, and there's a, if you're interested in this topic of the intersection of physics or cosmology and religion, the Templeton Prize is given every year for to somebody who's been prominent in writing about or bringing forth new ideas about that intersection between science and religion, principally in the astronomical field. And one of those winners is John Barrow, who I met on a cruise ship. He was a lecturer on a cruise that we took. And he's one of the fathers of this area of discussion, the anthropic principle. So if you're interested in this topic, there's the information in this section of this slide deck where you can go and look for books and other material about, are we living in a universe that was tuned for us or not? And must there be other universes, perhaps tuned so there are no observers? And so there's some discussion here. Once again, I have some other things I want to show you, so I'm not going to read all this. I want to get to a picture. Martin Rees, who was the Astronomer Royal of England, is now retired, he wrote a nice little book called Just Six Numbers that discusses the 6 numbers he thinks are critical. One is the density of the universe, what fraction of the universe is made of atoms, or atoms and dark matter. So in his book, which is now about 20 years old, he used the number of 0.3, which is pretty close to the number we have now. It's like 0.33. 33% of the universe is made of either dark matter or the stuff we're made of. He's got this number and just things. What fraction of the universe is was energy? And he's got that number pretty much right. And the whole book, which is only like 140 pages, is about if you change one of those numbers just a little bit, does that mean the universe ceases to be hospitable? So one particularly critical number is the expansion rate. I just mentioned if you use Casimir's theory of vacuum energy, you get a number for the universe that's wrong by a factor of 10 to the 120th. If the universe was expanding at the rate that you measure in the lab, we wouldn't be here. The universe would have been created, and the stuff in it the universe would be so stupendously huge that the distance between objects would be light years. An atom would never form, so we wouldn't be around to observe. So anyway, this is an intriguing topic, and fine-tuning is an issue. Was there fine-tuning? And you see, here's Martin Rees, has this book, Just Six Numbers. John Barrow, who I mentioned, wrote a classic over 20 years ago, over 30 years ago, on this. He and Tipler, and others. Now, this guy, Victor Stenger, this is an intriguing character. He lived in Boulder. He died maybe 5 years ago. He wrote this book called The Fallacy of Fine-Tuning. He is a serious astrophysicist. And he took the numbers that people had embraced as the numbers that matter, like Ries's 6 numbers. And he said, okay, suppose the electron mass was not what it is today, but it was twice that. Does that mean atoms wouldn't exist? And he did a bunch of arithmetic, which he summarizes in this book. And he says, yes, atoms would exist. They would be different. Chemistry would be different, but chemistry would still exist, and it would not preclude the evolution of animals leading up to humans. So Stenger actually goes through the arithmetic. You don't have to read about it. He just shows you the results, where he turns every knob. Like if the expansion rate was a little bigger, but the gravitational constant was a little smaller, you'd still get a stable universe. So this is a very valuable book if you're interested in the anthropic principle and how it is that humans are here. And there's Martin Rees's book, just 6 numbers. And there's some discussion here of the knobs that people can turn. The multiverses we've talked about a number of times. This is like Where's Waldo? One of the marbles that this little character is playing with is not the same. And the reason I have this cartoon here is it goes like this. Somewhere in the many universes that might exist, there's a room just like this room. There has to be, because if there's an infinite number of universes, everything is happening an infinite number of times. And it's just like this, and you are all here, and I'm here. The only difference is a small white dog walks in the room while I'm talking. And there's an infinite number of universes where the dog is not white, the dog is brown. Once you introduce infinity into the conversation, everything happens an infinite number of times. And in some of the cases, this is what the lecturer looks like. Not me. So this is kind of a metaphysical kind of a thing, but it's serious people are spending serious time on the question of multiverses. And one of the big players is Lisa Randall. This is a very interesting, I mentioned her last time, my friend used to date her and said, not a good girlfriend. But this article, it's in the New York Times. It's the people who think she's a genius are really eminent people. She's a very interesting character. So anyway, there's a link there if you want to do that thing. Drake equation I mentioned, we may not have time to do the calculation, but Frank Drake, I believe still alive, he's a pioneer radio astronomer, and he came up with a very interesting little exercise you can all do. He said, this is how you calculate the number of intelligent societies in our galaxy. You take the rate at which stars are being created in the galaxy times the probability that planets are orbiting these stars times the number of planets times the probability that life evolves, that there's enough time, the stability of that solar system is such that there's time for intelligent beings to evolve, times the probability that they evolve and care about building a civilization and that they have technology. And you can multiply the numbers together and you can get the probability that there's another intelligent life form in our galaxy, not the universe. So here's the definitions I just went through. I might have gotten a couple of them wrong. But you see what we're doing here. Oh, sorry. F is the probability that the society that might exist out there has technology for sending radio or similar stuff, times the length of time that that society survives before it kills itself by fighting with its neighbors. We do not have a good track record here on Earth. Society, I mean, stable societies last on an average of probably less than 1,000 years. You know, there were the Romans, and then there was the Goths, and here we are. We barely, modern society is, what, 300 years old, or 500 if you want to start with the first scientists. Anyway, you can do some arithmetic, and if you put in the numbers that have been measured, which we know are true, like the rate of production in our galaxy of new stars is 7 new stars per year. That number was not known when Frank Drake conjured up this equation. But we now know this. And what is the fraction of stars that have planets? 0.4 is too low. It's more like 1. There's no stars that we're able to study in detail that don't have planets. So you can put numbers in, and if you put the probability of intelligence is 1 in a billion and so forth, and the lifetime of a civilization is 300 years, blah, blah, you get a number that's approximately 0 for the probability that there's another intelligent society in the galaxy. On the other hand, if you use the numbers we know, 7 new stars and this and you have that you give them 1 billion years to do their work, then you get a number that's quite different. You get 36 million intelligent societies in the galaxy. And this is where Enrico Fermi stands up and says, where are they? Why haven't we seen them? So this is something fun to play with. So what this illustrates is there we are. This is not, obviously, we cannot take a picture of the Milky Way because we're inside of it, but we're kind of right there. And there's a sphere of radio signals that started kind of like 100 years ago when radio became prominent. There's a sphere of signals going out around our planet.
Yeah, but it's only 100 light years.
Exactly, that's the point. It's only 100 light years in radius. This is the hard to see this unless you do this at home, but because this has the names of the nearby stars that are within 50 light years of us. There's a few dozen.
Yeah, but if you suppose there was another Earth, the same size and shape as ours, the same place with respect to its sun, that came into existence at exactly the same time as ours, and then you have 4.5 billion years of development and evolution and appearance, life, and so forth, it's easy to conceive that a civilization that came up on that other planet would be 1,000 years ahead of us or 1,000 years behind us. And right now, having them, we not only have to know the right where to look, but we have to know the right when.
Right.
If we don't line up in the last 100 years or so, we could have been interrogated by some other civilization 1,000 years ago, and they'd think nobody's home.
Right. So, yeah, in fact, my friend Steve Kilston, who's an astronomer, retired astronomer, did his undergraduate dissertation with Carl Sagan at Harvard. And his thesis, he graduated probably 1966.
I thought Carl Sagan was from Cornell.
He was, but he was at Harvard before that, I think. So, what life form would somebody observe if they were looking at Earth with the technology that existed at the time? Telescopes that Steve could conceive of in the 1960s, and the life form that an extraterrestrial would have said, hey, that place is covered with cars. They would not have been able to see us, but they would have seen a thing the size of an automobile moving around. All right, I have one last thing for you. We talked about, and it's this. So we have not talked about any spiritual things in this class, but I want to give you something to think about related to life after death. You've all heard that in a few billion years, the sun will become a red giant as it comes near the end of its life, and it will get bigger. And it will, there's some drawings here that illustrate how big it will get. It will get to the star itself will be a little bit bigger than the size of Earth's orbit. So Earth will become part of the star. And the question, everything on Earth will be incinerated and become part of these swirling mass of stuff that's in the star. And over here, this is a bunch of arithmetic I did. I solved the following problem. If you have in your lifetime 100 people that are close to you, that you care about and care about you, there's a certain mass involved, there's a certain number of atoms, and those atoms will be now part of the big red giant star, and they'll be surging around. And the question is, how frequently will an atom of one of your beloved go right past you? This is my approach to life after death. And the answer is down in the lower right, 650 times a second. An atom from somebody you cared about, and Elvis, and Mahatma Gandhi, and Julius Caesar, all of that stuff. 650 times a second, an atom of that person will go past one of your atoms. You will be eternally surrounded by, embraced by everybody you cared about.
Well, also Hitler.
Hitler
The
and,
Tsar.
right, and the stones they used to make this building and so forth. But it's not like,
Harvey Weinstein.
yes, you and Harvey would be in a close embrace. But this is the way I think about when people want to have a conversation with me about life after death. I say, we won't be dead. We'll all be part of the same thing. And this star will eventually cool off, and it's not quite massive enough to become a neutron star. Oh, by the way, one quick thing. Those hexaquark structures were also in the news yesterday as a possible material structure deep inside of neutron stars. That's brand new thinking that somebody has proposed, because that is also a mystery. The neutron star is all neutrons, but the pressures at some point are so big that the neutrons get distorted. And so there's a proposal that hexaquarks are involved. So hexaquarks going to be in the news. So anyway, this is my way to think about life after death. You'll never be alone. Yes, sir.
Somewhere along the way, the ice that's thought to be on Mars might melt, and we might have life on Mars while we incinerate.
Here's the problem. Mars is too close. So if you look at this drawing, Mars would be very close to this new giant star. And there's another problem. That giant star is not going to last long. It took probably in the vicinity of 3 billion years before our solar system formed. And then we had this planet's been around for 4.5 billion years. The red giant life is unpredictable because it's not a dynamically stable star. So it'll gradually just fade away, maybe a white dwarf in the end. Depends on how much material falls into it. Folks, it's been great talking to you for the last I can't believe it's been 2 months. But like I said, if people are asking you what classes to take in the fall, I'll probably be teaching this again. It'll be better because of the questions you've asked. And for that, I thank you. And all the others who were not able to be here today. So,
Thank you.
Yes, and I open for me.
and I congratulate you all too. Because you're now, the stuff you now know, the vocabulary you know now is only known to a tiny, tiny, tiny fraction of our society. So keep looking up, as, to quote Neil Tyson.
Keep looking at that phrase.